Good morning. Thank you, Professor Forsted, for the introduction. I'm delighted to be here and deeply honoured to be here to give you this plenary lecture. My slight hesitation here is that I have my notes in front of me and they're sitting in the computer, and it's on a delightful angle where the coefficient of friction is not quite enough to hold it steady. So if I pick my hands up to wave it, the next thing that happens is my notes will be on the floor. So I will be one-handed this morning. What I would like to do is talk not just about the need for flotation as one of the pillars of mineral processing, but really to talk about the future of mineral processing per se. I'm very grateful to the opening comments at the start of the Congress, where we had an excellent plenary and some excellent comments which were very much in line with what I will talk about today, the falling grades, the energy, the environmental concerns, and so on. And really what I would like you to think about is how much has mineral processing got to change? Just incremental or fairly major change? And that will be the whole theme of this morning. We will note actually even one slide that was used in the plenary yesterday is identical to what you will see this morning. I will cover three parts, and the third part will in fact be the most content. I want to look at in how mineral processing must change, look at the drivers for change in mineral processing. And the first point I'd make is that mineral processing has always been about the raw materials that we have to improve through mineral processing. That has always been the case for a long time. We heard yesterday mention of the golden fleece. There's evidence, and I refer you to Professor Hadashi's history of mineral processing. There's evidence that the golden fleece is actually a very good technique for recovering gold. And as Hadashi has pointed out, even the ancient Egyptians knew that gold was easier to recover from certain ores, rich ores, than from lean ores. And we're all familiar with the wonderful works of Agricola as published in De Re Metallica. I had the honour of working for a company for some years who had an original copy of De Re Metallica. There aren't many of them around. Quite strikingly, if I just stay on the ancient Egyptians for a moment, there's actual steel artefacts found from Egypt. And you think about this, how on earth did they make them? And the answer is it came from meteoric material. Just emphasising this point that mineral processing, to come through to metals in most cases, is very much about the raw materials that you have at your disposal. Now, moving on to the macroeconomics and what drives mineral processing. We had yesterday some graphs of the increasing consumption of copper, of iron or steel as it was, and a range of minerals and metals. And the underlying driver of this is, of course, the increase in the economic state of individuals and of countries. What I've shown here is some data that's some of the best data around is actually from Philip Crowson, who was the chief economist for Rio Tinto for many, many years, as many of you know. And his data, along with many others, shows that as gross domestic product goes up, so the consumption goes up and then eventually it falls off again. And his data there is specifically for copper, but we could also put up similar graphs for almost any commodity that you can think of. And the point is, of course, that there are many, many countries, and large ones at that, who are still on the left-hand side of the curve. They are still on the part of the curve where increases in GDP will cause an increase in the use of commodities. Now, this is nothing to do with the right-hand side, where ultimately, in a circular economy, the demand for new materials is low, perhaps approaching zero. But that's a separate argument, of course, which is not the topic of the talk today. So GDP drives demand. There's very little doubt on this. And if we then unravel it a bit further and look at the drivers... Oh, okay. Well, that's because I'm not doing this. I'll just give you a chance to catch up. There's the steel in the Bronze Age from meteoric sources. And there's the Philip Crowson data. And now you're as up to date as I am. So these are the drivers, strong drivers of GDP growth. It's essentially urbanisation. If you just want to do it at a correlation level, it's almost complete. Now, urbanisation would seem to be a trend that is unstoppable. I would suggest to you that you only have to look at the percentage of people needed for agriculture, country by country, and you'll see that it tracks with GDP. As GDP goes up, the number of people required for agriculture goes down. Even in China now, which has been one of the countries where farm size going up, which means less people in the country, has been happening for many, many years. You'll find when farmers retire, they sell or lease their farms out, and this is part of this rationalisation process. The only country that I'm aware of where farm size is still going down is India. And that's actually quite a significant challenge and a problem. But urbanisation is happening around the world, and for the countries that were on the left-hand side of that Philip Crowson curve, that translates through to increase in demand. So as mineral processors, you should be very happy. It means that your services are in high demand. Let's move on. Now, I'm going to stay with copper. And the interesting thing here, and where I'll digress slightly from the plenary yesterday, is that there is no doubt about the demand curve and the increase in the consumption of copper. But what you saw yesterday in the plenary was the curve showing the raw cost of copper increasing very much over this same time period. But what I've done here is show it in real terms, that is, inflation-adjusted terms. And the intriguing thing there is that you can either take a very macroscopic economic view and say over a 100-year period, the real cost of copper has come down. Or if you're slightly less sanguine on macroeconomics, you would say, okay, open cut mining and flotation revolutionised copper production. And if you look carefully at the graph, you'll see that even with the First World War, the cost in real terms of copper came down most dramatically. And you can argue that that was largely technology. And since then, it hasn't really risen much. Now that's an interesting way of looking at the drivers for mineral processing. You might even argue that the definition of a commodity is something whose price in real terms falls forever. There's 200 years of data of a basket of commodities in real terms, that is, inflation adjusted. And it's fairly dramatic. You would be fairly hard pressed to say that the price of commodities is rising against that data there. It's falling. And you good people are responsible for that. There is no global scarcity of resources. Otherwise there'd be price increases in real terms. That's very simple economics. Or there'd be massive substitution. And the reason the price falls, more or less continuously, is because of innovation. It's because we have IMPCs and because we have people working to improve how we go about mineral processing. There's 200 years of results of that effort. Just for completeness, I refer to a recent roadmap for copper, which was done by the Warren Centre, and their two main conclusions were that the increase in demand is simply driven by urbanisation, which I've already suggested, and that as for energy, which a certain law of thermodynamics tells us cannot be substituted, there is currently no major technical substitute for copper. So if I stay with the theme of copper, it's a very good place to be. Now for some of the downsides on drivers. Here is the grade of copper projected out to the year 2025. And you can well question, how can you project grades forward that far? And the answer is very simple. It takes time to bring on major deposits, or even time to bring on hundreds of small deposits, so that we already know what are the major deposits that are being developed. And they take 5 to 10 years before they come on stream. So as a consequence, we can fairly well predict the forward grade of copper through to at least 2025, assuming no major substitution. And I've already suggested studies indicate no major substitution by 2025. Now this graph then is actually very bad news for mineral processing, because if I turn to the work of John Marsden, who's sitting with us today and will be giving a plenary tomorrow, this is some of his work, and it's a very solid background. He is here and can give the details of it himself if you want further details. But what he's showing, and I think that it's absolutely right, is that as grade goes down, so the energy consumption of no matter what your process is, the energy consumption goes up. And of course you can always switch from one process to another, but that costs you capital and involves different recoveries. You start off a mine with a certain process in mind because it represents the best economics. Then as grade falls, your margins fall, inevitably. And that's not just the Marsden theory. John Marsden has done a lot of work, technico-economic modelling and detailed at that, to come up with this data. So I remind you again of the world grade, if I just go back. And you see it's coming down towards 0.9% in 2025. Jumping ahead onto Mr. Marsden's work there, then you can see this is heading into the territory where if you thought energy costs are rising and energy demand is rising, it's going to get a lot worse, not better. So this is a challenge for mineral processing. Now, as was also covered in yesterday's plenary, I would suggest to you that copper is not alone. This is some data from CSIRO. Global data is actually quite hard to come by here. So this is not necessarily the most recent, but it's long-term data. And the point is the same, that global grades for mined commodities are falling and have broadly been falling for the best part of a century, if not centuries. So most of us know that we're following grade curves down, and this is a challenge. I would argue that essentially the massive increase in the size of flotation units, and it is massive. There's data up to 2012. I couldn't get any more recent data, but perhaps Mr. Marsden tomorrow might comment on that. I would argue that this massive increase in size is, of course, got a lot of innovation embedded in it, but it's been driven by need. The falling grade means that we need much more grinding and flotation, and this is one of the responses. Flotation, I'd remind you, has had well over 100 years of R&D, and you can argue that the performance increase that we've seen is in some ways quite staggering from the early results. It's not just the size of cells, it's the energy requirement. It's our understanding of the fundamentals, courtesy of a long string of people. Fine particle flotation is now practiced. When I worked for Rio Tinto and the Century zinc deposit was found, the one problem with that deposit was that it had fine-grained silica in it. And this fine-grained silica, the liberation size was of order 7 micron. And the team that was working with me at the time dismissed this deposit as being uneconomic on the grounds that you could not, on million-ton per annum scale, grind and float with a liberation size of 7 micron. In fact, the team very quickly discovered that you could, and it's just that the residence time in Ruffers, for example, was over an hour, and so it went on. Fine particle flotation is now quite routine at high tonnage scales. It had always been practiced for many years, I might add, in industrial minerals. So the question remains, overall, from these macroeconomic drivers, is the sort of progress that we've seen, which in the last 50 years has been largely incremental, is that enough against this tide of falling grades and rising costs? We might turn to another total aspect, which is automation, deep data, data mining, data analytics. Every mining company in the world knows how to spell these words. Many mining companies use them. I would suggest to you, from an artificial intelligence point of view, that we're still only scratching the surface, with due respect to the many companies involved here. Compared with the oil and gas industries and some others, we've still got quite some way to go. But these are new technologies, they are being applied, and of ever-increasing scale. We now regard it as normal to see autonomous trucks that have no cabin, and some of them can tip forwards and backwards to save the small amount of time that's involved in reversing in to a shovel or to a dump pocket. So, again, are these major developments enough to meet the challenges? I'm using here publicly available BHP Bulletin data so that I can't be accused of making this up. Here's BHP Bulletin's water use in Chile. Now, the normal thing with improvements in technology and innovation is that your unit consumptions go down. Water use in Chile is heading in the wrong direction. Okay, thank you. I don't know why. The answer is I've got to press the button much harder. Watch this space, the computer might fall off. Water use in Chile is heading in the wrong direction. This is publicly available data. This is not my data. And indeed, again, this is publicly available data. This is BHP Bulletin's projection of costs out to 2025. It's their copper cost curve. And it shows no improvement over a 10-year period. So at best, you might argue that in copper, and this is the world's leading copper producer, we're standing still. And I'd suggest to you that's not a healthy position to be in. Let's move on. Here's one of the reasons. Labour productivity, and these are figures, both BHP Bulletins and my own from the Australian government. Labour productivity in the industry has decreased by over 20% in the last decade. That's the wrong direction. Well, we might question, are our improvements enough? And that sort of data there, macroeconomic data says, no, afraid not. And finally, in terms of macroeconomics, exploration seems unlikely to reverse the trend. For those of you who are very sharp and with good memories, this is the identical slide to the one used by Professor Bortnikov yesterday. And his point and my point are identical. Exploration is not producing the major discoveries at the rate of previous years. Simple as that. Now, we all know the geologists tell us, and I'm quite prepared to believe them, that there are still very major deposits significantly deeper than where we've been looking. And that means that the exploration techniques, be they gravity gradiometry or whatever, have to be improved to be able to find them. I remind you that a relatively recent discovery in Arizona was made at a depth of 1,000 meters. And it was only made because somebody in picking up a property that had been sold, had been mined out down to 700 meters, decided to sink another hole 300 meters further down from the lowest that was there, and found the top of a very large porphyry deposit. Totally buried, 1 kilometre deep. So I'm sure the geologists are right that there's a lot more there, but what's happening at the moment is that they're not discovering them. So we're left with falling grades, rising energy, rising water requirements, and I suggest we have to do something about it. The biggest factor that people are using at the moment, and the biggest method, the most powerful method, the game changer, I think, by and large, is of course to sort, one way or another, or to separate early. The earlier the better. All the way through to the geometallurgical approach of very much selective mining based on grade. And the more you can do this, of course, the better the capital productivity. Similarly, at the other end, a coarse flotation. This is some work from some modelling by Jamison, that as we can now float coarser particles, and he's not going particularly coarse here, you can, of course, do far better on energy and costs. So these trends are happening, and perhaps will be enough. So let's look at our journey so far and finish off this side of things. We have some clear targets for where we will head, and separation of the face or earlier is one of them. But we face some very strong headwinds. Now, I now want to turn to something totally different. And for those of you that are watching the clock, I understand that you only had one plenary this morning, not two. So I'm allowing the time to slip a little bit, but I won't run too much over time. I want to look at the social license to operate and the whole future of mining. So this is where we put our thinking caps on and we jump forward. No, I'll stay on Hitch and Dunbar. Hitch and Dunbar ask a very interesting question in terms of sustainability. They turn it on its head and suggest, actually, is mining as we know it sustainable? Can you consider that in the future you will make a large hole in the ground, dig up a lot of material, spread 99% of it plus on the ground somewhere, just to get the 1% out? Can you consider that as impossible, that will be allowable? And there are many who are arguing, no, actually, probably not. You really have to consider that mining will have almost no environmental footprint as the future. And I'm going to get on to that. I do think that that is a future. I was interested to note that 2 years ago at the World Economic Forum in Davos, they actually had a session on must mining change? My words, not theirs. And the print is too small to read, so I will reverse it. And they're suggesting the drivers of change, the higher demand for fairness spread around people, the increasing democratisation, the growing concern for the environment, the abrupt generational change. If I look around this room and say, what's the proportion of millennials in the room as compared with the population as a whole, then they're seriously underrepresented at this IMPC. There is an abrupt change, generational change. The intensified rate of technological change. The reason that the rate of change of technology is increasing is actually very fundamental. All technological change builds on information that you, the person making the innovation, have access to, or in your head, or from your colleagues. Ergo, it follows that the more change that happens, the faster change will happen. It's actually quite simple. It's a fundamental of innovation. Mind you, we are fairly good at forgetting sometimes as to what has been done. Likewise, geographical shifts, and likewise, a topic that the IMPC has often looked at, rising concerns about artisanal mining. I'm reminded from my days in Rio Tinto of artisanal mining and what a problem it can be. One particular example, as soon as an area was pegged out for a gold development, immediately there was, within weeks, a population of some tens of thousands, totally unsustainable, trying to make a living out of societal gold, of which there was a small amount, I might add. And that was just an unsustainable artisanal mining situation. So there are major changes afoot which are more from the society end rather than just the techno-economic drivers that will cause change. Now, in terms of the social license to operate, this really is a growing issue. We're all aware of these issues. but the magnitude is actually quite extraordinary. I have data, not on a slide, that says in 2008, if we look at the oil and gas projects, for which there's very good data, in the preceding 10 years, the time to bring on a project doubled. And I'd suggest to you, from my experience in the industry, the same applies for mining and metalliferous activities. The study that I refer to here is from Franks et al., and they looked at 50 major projects around the world in recent years. And these were not small projects. Some of them were up to $3 billion expenditure. Most of them were in the hundreds of millions of dollars capital expenditure. 50 major projects in the last, I think it was 10 years, and published this in 2014. And what they showed was that the delays coming from the social license to operate side cost many of these projects $20 million per week, that sort of order. Now, not only that, what is, you might say that was the good news. The bad news side was that the conflicts often escalate, and the conflicts in over 20% of those 50 projects escalated to the point where it wasn't just campaigns and procedures in court and so forth. They escalated to physical violence or physical conflict, resulting even in death. And a number of those projects, 20% of them, remember these are major projects, were abandoned. So this is a very strong driver. It says ignore public license to operate at your peril. You are running an 80% chance that you might get through, but with delays. There are some new approaches, There are some new approaches to gaining the social license to operate, and I would suggest to you that the first 3 points there we're all familiar with. The need to outline what you want to do to the public and give them the opportunity to engage. The company has to commit to doing this. It can't be the greenwash department. It has to be clear from the top and through all of the project team that there's a commitment to engagement. And it goes without saying that there has to be adherence to government regulations, whatever they are. But what this CSIRO study has shown is that if you really want to increase your chance for getting the public license to operate, you actually have to give the community the opportunity to say how the project should go. And this is not just about how royalties are distributed. It might be as to whether the company sees this as a step towards a circular economy, for example, and whether the processing facilities that are put in will ultimately be running on recycled materials rather than new materials, or whatever. And that step, the CSIRO study has shown, of actively seeking community contributions, not financial, but intellectual, to a project, significantly increases the chance of getting the social license. I'm not quite sure where I should be pointing this. Do I point it there? No, that doesn't work. Okay. So our journey today, we've looked at macroeconomics, we've talked a little bit about social license to operate, and the third and final part is about on why Inplace recovery, and it goes under several names, is, I think, much nearer than many people think. And if it is, then mineral processing as we know it, flotation included, disappears. And as Professor Dave Deglong remarked to us yesterday, I think it was, I was talking this message of the IMPC way back in Cape Town, which is perfectly true. But what I want to say today is that I think it is much nearer than many of us would think. So let's run through this. And I have some advice on where I should be pointing it. Okay, we've got it. So this is what I said at the IMPC in 2003, that the mine of the future would look like this: deep, fractured by caving, in-place leaching, using advanced biohydrometallurgy and the copper one electrochemically underground. So the only thing you bring to the surface is the copper. Simple as that. Almost no environmental footprint and almost no environmental impact. That's what I said in 2003. Now I want to take you on a small journey to suggest that this is closer. So the ultimate step is in situ recovery. And because it's difficult to read the colours on this, this is just a schematic of in situ recovery. But I would remind you that it's not simply a case of putting in one well and having another well for extraction. It is all about observation wells, for hydraulic control wells, recovery wells, injection wells, rinse wells for clean water injection, and rinse wells for dirty water recovery. It is very much a complex chemical process. It is not simple mining as we currently have. Now, why is it so attractive? It's fairly obvious. The reduced mining and comminution costs, they are eliminated. The potential for treatment of low-grade materials. You don't sterilise the rest of the deposit. You're working on one part of the deposit at a time. And this reduction or even elimination of land disturbance. I'd remind you of in situ recovery. So I'm told, I don't have the data for this. References to it date back to 177 BC. The Chinese used in situ recovery for copper back in 907 AD. By the way, nature did it for us, and the Romans were aware of it and profited from it in the river in Spain called Rio Tinto, with its acid mine drainage. So ISR is routinely applied for water-soluble salts, for some minerals, especially uranium and lithium, I think we're all well aware of. But its uptake for hard rock minerals so far is very minimal, and I want to explore that a little bit. But let's just look at uranium. Many people are well aware that in situ recovery is commonplace in uranium. They're perhaps not so aware of the fact that over 50% of the world's uranium is now mined by in situ recovery. Over 50%. And this has been quite a change since the year 2000. So in situ recovery is picking up in some areas really quite rapidly. And the reason why is essentially because it's the lowest cost and the environmental footprint is under control and is minimal compared with other methods of mining. So I would suggest to you that this is a forward predictor of what's going to happen for many other minerals. So we might well question why the limited uptake for hard rock minerals. And as somebody who's always been involved for their working life with new technology, there are concerns, and rightly so too. People are concerned about how the leach solution is contained, how to guarantee no significant impact on groundwater. These are very legitimate concerns. If any of you want a business proposition today, I'll make you one. I can take you to somewhere where there is roughly 50 tonnes of gold at no more than 200 metres deep, spread out, by the way, over about 50 kilometres, so you can do your own grade calculations, and it's in deep leads, underground rivers. It comes from an area where the alluvial gold near the surface was mined last century and produced a few hundred tonnes of gold. And from the little bit of exploration done, we know quite well that there's a similar amount of gold, no more than a couple of hundred metres deep. Now the challenge is that it's in flowing rivers of fresh water, and those rivers are used for agricultural purposes, and so if you were going to leach the gold out, you have got to think about how on earth can you do that? What barrier technology is absolutely and solidly proven and no chance of a mistake? But if you're interested in that one, we can talk afterwards. I can show you exactly where these deep leads are. It's a challenge. It was my first challenge on joining Rio Tinto, I might add, a long, long time ago, was to figure out how to mine the deep leads. And the simple answer is yes, you can. Technologically, we developed barriers that could be put in and then later dissolved. But getting the public licence to operate was seen as somewhat difficult, so it was left. So the way forwards, I see it, is that intermediate steps are possible, and they will be used to prove things up as we go. That in situ recovery and hard rock is very different to conventional mining. But intermediate steps are possible. Oh, this one works very well. We'll now be able to speed up. ISR is much more like a... Thank you very much. ISR is much more like a chemical process than mineral processing as we know it. This is taken from a company which is practicing ISR. And what they're arguing is it's all to do with reservoir and reservoir engineering. It's a chemical process. The thing to point out is that there are steps to ISR. You won't be able to read the fine detail on that, and it doesn't matter because we'll cover it. And they're essentially what CSIRO actually is using terminology: inline recovery, in-mine recovery, and in situ recovery. And I've already talked a little bit about in situ recovery. Let's look at what we mean by in-line recovery and in-mine recovery, both of which are steps on a learning curve through to in situ recovery. So can we have the next? That's good. So by in-mine recovery, and this has been practiced already, there are some good examples of it. We mean by having equipment underground, very much selective precision mining, pre-concentration of the face, ore sorting technologies underground, and underground modular plants, the sort of plants which Gecko from Ballarat produce. This is already happening, and it teaches us a lot and moves us along the way. In mine recovery is very much like the vision that I put up in 2003, and this also is now being approached in some places. It's once you have caved some material, and perhaps you've taken out as much as you wish to, you essentially look at leaching in place. Again, the permeability that you can get, the barriers, the hydraulic monitoring, all sorts of things have to come in. But it's something which is a very big step along the way to in situ recovery. And for hard rock projects, this is an obvious follow-up for block caving. So, some progress on technology developments. I point out that recent progress is really very significant, and we'll look at some of these in more detail. I've mentioned just one here, which some of you will be familiar with. One of the problems with leaching some copper minerals is that they passivate very quickly. But there are tricks around this, not the least of which is to vary the EH and pH conditions cyclically. And one, if you like, does a certain amount of leaching and passivates, then one attacks the passive surface and then repeats the process. There are all sorts of things we're learning, particularly at the higher temperatures involved in situ recovery. There's so much now that we can take from the oil and gas industry, as the next few slides will show. The control of the lixiviant is, of course, a top priority. I'm very much a fan of injectable barriers as being one of the ways that you control the spread of the lixiviant. We did a lot of work on injectable barriers, and these can either be active or passive barriers. Plus one can look at dissolving them or changing them or leaving them if they're totally inert, such as silica gel, for example. The monitoring and in-place monitoring is absolutely essential. But nowadays we can look at sensors which we place into the mat or into the surrounds, which will stay there and have longevity of tens of years to do the monitoring that's so necessary. There is so much happening on all of the peripheral aspects that I'm very confident we will see in situ recovery speeding up just the way we have seen it in the last 10 years for uranium. Some other examples of game changers. I'm indebted to Orica, who have supplied us with some data, some of which is, of course, in the public domain, and some of which probably soon will be. One of the points is that we can now envisage very different explosives being set off in a series by electronic ignition with no wiring required, all remote. And this is a bit of a game changer. When you couple this with high-fidelity blast models, the sort of thing that you can do is put a borehole up from a riser through a block cave material, quite large diameter, as a preconditioning blast hole, and then you can set off a series of charges, some of which are about generating macro properties, and some of which are about generating micro properties. And this has now been tried for not a block caved material, but for a horizontal sandstone strata, and shown to be quite effective at rubberizing it and producing a size distribution appropriate for in situ recovery. So there are game changers going on here. Another one is small diameter steerable drilling. We're all well familiar with steerable drilling in the oil and gas industry, but that's very large diameter and very expensive in comparison with what we can afford to be doing in mineral deposits. Remember that the oil and gas industry does things like a few $1 million for one borehole log that are just not in the economic envelope relevant to hard rock minerals. But I find this particular work on small, steerable drilling and fracking, I might add, to be a game changer. I would argue that the modelling, largely courtesy of our friends in the oil and gas industry and the extensive fracking that they've been doing for over 100 years, I might add, and the modelling of it, much of this comes straight through into the mineral and metalliferous industries. Similarly, there are new stimulation technologies. I'm not a particular fan of the so-called Naturofrac pulse combustion formation stimulation technology, so this is not a free advertisement for them. I've simply put it on the slide because as an example of people who are arguing that there are many stimulation technologies around now, and they are not crude like some of the early stimulation. I remind you, just as an aside, that the first recorded stimulation technology was in 1860, when an oil well in Pennsylvania eased up on its flow rate. Someone had the idea of dropping to the bottom of the hole a stick of dynamite. It blew up at the bottom of the hole and the oil well flowed again. That's the first known example of fracking, as we would call it today, or stimulation to use a better term. So it's been around a long time, at least since 1860. I'm suggesting to you that it is now much more a science and relevant for our in-situ recovery. So copper and gold have been the trailblazers, I think, in eliminating mineral processing. There are numerous examples of leaching in place after blasting, both primary and secondary sulfides, often after other mining has been completed. In situ recovery, there are commercial operations here in Russia, and two that I'm aware of, Florence and Gunnison in the US. And part of this is all happening because our understanding, I mentioned the passivation of surfaces, our understanding of secondary product formation and how you can control it is very rapidly advancing. And this actually should be a topic for the IMPC to report on, because it is a game changer. I'll finish just by showing a couple of slides from the commercial operations. The case study one is Florence Copper. This is a commercial effort looking at producing, you can read the figures there, for 6 years, £55 million annually, and then another 14 years at £85 million, 25-year project. And it's been done after 2 years of running a test facility and pilot-scale demonstration. And what they've shown is that they can contain the lixiviants and do so reliably. That's the key to in-situ recovery. This is not very deep, of course, and that's the nature, I think, of when major new technologies come in. The so-called low-hanging fruit, or in this case, not very deep-bearing fruit, are the first targets. Excelsior Mining, the Gunnison project, is the other one that I would mention. It's an ex-Magna Copper project, and similarly, it's really very minimal environmental footprint. That's one of the keys. So let me wind up. Slightly over time, but then I think you only have one plenary today and not two. I would argue that in situ recovery is happening. But the bigger prize is still to come. The deep, fractured by caving or by directional drilling and cracking and in-place leaching using very advanced biohydrometallurgy and copper one electrochemically underground, that is still to come. But is it 2 years off? Won't be 2 years because nobody's doing enough homework on it yet. I would suggest to you it's well under 20 years. Mind you, that's fairly similar to what I said almost 20 years ago. So, in-place recovery to replace mineral processing in general and flotation in particular has been predicted for many years. And I'm suggesting to you two factors in conclusion that will combine to suggest it will happen within the next 20 years. The pressures of increasing costs, declining grades, and ever more demand socially and environmentally, and that the individual steps that are needed are all being developed and being developed at a pace. precise geology, chemistry, rock properties, hydrogeology and other local factors all combined, so that in situ recovery is not just a simple technological magic bullet. There's a lot of work and a lot of things that have to fall into place before you can say that in situ recovery is the way to go. Now, I would refer to Professor Marcus Reuter's work and his excellent presentation yesterday concerning minerals or materials. One has to define our terms in circular economies. The things that are necessary to recover materials, one of the ways forward does involve much of what we would call mineral processing. So from that point of view, you can argue mineral processing has a long future. But it might also be that in the future, at least all of the new materials that we need are essentially won by in situ recovery. So I thank you for your attention. I've run slightly over time as was permitted, and I hope I've managed to convince you that in situ recovery is going to replace a lot of what we're talking about at this conference. Thank you, Chair.